So for our project, we worked on data-to-text generation of beer reviews. So basically, the main point was to explore the task of data-to-text generation, which involves generating fluent summary of structured data. And in our case, the structured data was beer reviews. So we used the Rate Beer dataset, which consisted of 3 million text reviews, attribute ratings, and overall ratings of beers. So concretely, given discrete attributes such as beer ID, user ID, and certain numerical ratings of appearance, aroma, palate, and taste of beers, can we output a user review? The novelty of this is that discrete attributes describing beer are latent. So given only the rating of aroma, we still have to generate a review that actually describes the aroma. So we hope that our model basically learns by linking attributes to beer IDs. And the way we partitioned our train valve test split was so that each beer ID was, so that each of these splits contained all beer IDs.
So we used the sequence-to-sequence model to generate the reviews. As input, our model would take in a sequence of tokens that identify the beer, the brewer, the reviewer, and the corresponding ratings for the attributes of the beer. For example, if we wanted to describe the beer ID 61510 with the corresponding brewer and style, this is how we would represent it. The outputs would be the tokens of the reviews, and we would use standard cross-entropy loss to maximize the likelihood of the next token in the review given the inputs and the previous tokens predicted. We explored several variants of seek-to-seek models. We used a recurrent neural network, a convolutional neural network, and a transformer architecture. For all these architectures, we used 2 layers and typically kept the input and hidden sizes of around 512. For non-recurrent architectures, we also use positional encodings so that the model knows where the inputs are. We kept the top 50,000 input-output tokens in the vocabulary as a pre-processing step. For decoding, we use the beam size of 5. So in terms of qualitative results, we found that the RNN model significantly outperformed the other 2, which were the transformer and the CNN, in all the automated metrics we looked at, which included blue and rouge scores. We found that the transformer performed the worst out of all of these. Specifically, we weren't even able to get the perplexity down or training to converge. And one of the reasons why is we think that the memory component of the RNN and the very concrete position of the token in the input makes a big difference. And RNNs might be able to encode that dependency better than CNNs or the transformers, which rely on another embedding for inputs. Also, we found out that what we wanted to test was whether the RNN would just spit out the same review over and over again, or whether there were diversities in its predictions. And to test that, we looked at the blue score of the RNN on its test predictions and randomly sampled input beer IDs and attributes, and we found that the blue score between these 2 things was 2.75, so it's quite low.
So looking at some qualitative results for the RNN, given the ground truth here and the prediction from the RNN, we can see that there's some semantic similarities. So for example, both talk about creamy off-white heads, laced, and aroma. With the CNN, you can also see that it talks about creamy off-white head, but it's not as good as the RNN. It doesn't bring up the same amount of semantic information. The transformer is the worst. You can see that it gets stuck in this kind of loop of predicting sweet and. So I guess future work will be definitely deepening semantic relevance of beer attributes and generated reviews, and finding better metrics to actually determine the semantic relevance of generated reviews with the attributes given. And lastly, eliminating the generation of non-coherent reviews, which we saw in the transformer model. Thank you.